Okay, now recording. All right, so it's been a while since we met, a week, just literally. So when we left off last Thursday, we were at 14.5 and some of 14.6, and I even did a little bit of 14.6. So I'm going to finish 14.6, sneak in some of 14.7 hopefully today. Okay. And at a slow rate, I would finish 14.8 by next Thursday. So let's set the date for the next exam to be Thursday, the 18th. Originally on schedule, it was on the 23rd. Let's set it in stone as the 18th. And we're not that as far ahead as you might think because, okay, for this exam, and I'm leaning toward this for all the other exams, I'm gonna let you have the entire class period for it. Okay, some problems are just so long, you need that much time to do the problems. Okay, so I'm leaning toward exam 3, 4, 5, and the final exam, of course, for being the entire class period. Okay, so for this one, for sure, you can have the entire class for exam 3. So that means once we start at what, 6:10, okay, I'll put in Canvas announcements, the exam, and you can just get started. And you have the entire class period from what, 6:10 to 8:25 to do the exam, okay? Which means any questions and answers have to be all in by Tuesday, 3/16. Okay, so I'll try to reserve you some time for questions and answers on Tuesday, March the 16th. Okay, assuming even at a slower pace that I'd finish everything by next Thursday, maybe even Tuesday. Okay. All right, so coverage will be chapter 14, which is everything here, here. And you should know the rules by now, since you've already had a couple of exams, in terms of you must submit at least 70% of the homework. I end up doing a huge percentage of the homework anyway, so it's not that hard to do all that. Usual rules on exams. So I closed the exam at what, 8:25? So you take pictures on your cell phone or scan and so forth. Get it to me by 8:30, and homework has to be in by 9 o'clock. But again, I'll take it early. So again, as soon as class is over on what, Tuesday the 16th, March 16th. So after class on 3/16, you can start turning in the homework early if you wish. Okay, but again, I may very well go ahead and get started with chapter 15. Okay, so I think we're ahead, but not as far ahead as we think. We lost a little bit from the flex day. And again, I'm trying to push everything back so I can give you the last exam on what, Thursday, May the 13th, I guess. Okay. All right, so for this exam, the entire class, I'm leaning toward that for exam 4 and 5. And well, obviously you have to have that for the final exam, but definitely for this exam, you can have the entire class period, okay? So on the 18th, that's all we're gonna do. We're just gonna have the test. So any questions and answers has to be done on the 16th, okay? So any quick questions about that, please? You can either mute yourself or put it in the chat. Right, well, you can ask later also. Okay, let's get back to where we were. Okay, so we were on 14.6. I introduced it and did a few problems, but let's go back to it. It's been a long time since we've met. So key theorems, put on your formula sheet. Again, you can have one formula sheet, 8.5 by 11, double-sided, put anything you want. Okay, so directional derivative, page 948. Derivative of f in the direction of a unit vector u is partial with respect to x times a plus partial with respect to y, b, and if there's a z component, fz at xy of c. So that's a 3D version. Okay, you have to have a unit vector, so if they don't give you a unit vector, make it a unit vector. Okay. And then we have a definition of a gradient vector. Okay, gradient vector is del f is partial of f with respect to x, partial of f with respect to y. If you have another dimension, partial of f with respect to z, fx, fy, fz. Okay, in fact, here's a 3-dimensional version. If you had to put just one thing on your cheat sheet, I would do the 3-dimensional versions, like 13. Del f, gradient of f is fx, fy, fz, or partial of f with respect to xi plus partial of f with respect to yj plus partial of f with respect to zk. In which case you can say the derivative of f in the direction of u, 3-dimension, is del f dot u, unit vector, okay, in the direction of the unit vector u. Okay. And what's so good about having the gradient vector? Page 952. Okay, the maximum value of the directional derivative. So which way do I go to get the maximum rate of change? Okay, so the picture I was showing you was if you happen to be on that page. Sorry. Yeah, you're standing on a hillside. Okay, you're standing here somewhere. Okay, which way do I go? That way, that way, that way, which will have the maximum rate of change, the maximum value of the derivative. Okay, this theorem says the maximum rate of change is the magnitude of the gradient vector, and it occurs in the same direction as the gradient vector, the direction of the gradient. Okay. All right, and then we had the formula for tangent planes to level surfaces on 954. Okay, and that's if you have f of x, y, z equals 0. F of x, y, z is a constant. You know, I said 0. You can just subtract the k over, and then it'd be 0. Okay, and here is the tangent plane. Okay, it's basically fx, x minus x0 plus fy, y minus y0 plus fz, z minus z0. Okay, and then the normal line looks like it's symmetric equations. X minus x0 over fx equals y minus y0 over fy equals z minus z0 over fz. Okay, so that's where we were. Okay, I only did a couple problems last time, so I'll do a bunch more. And there we go. Okay, so last time, I believe I got up to 9. So 13, please. G of s and t is s radical t. At the point 2, 4, the direction is 2i minus j. Okay, so find the directional derivative of this function at that point in this direction. So first, if they give me a direction, first you have to make it into a unit vector. Okay, so unit vector u is 2, -1 divided by square root of 2 squared plus -1 squared, that's radical 5. So the unit vector is 2 radical 5, -1 over radical 5. Okay. All right, then I get the gradient vector, del G. Okay, it's the partial with respect to s, partial with respect to t. What's the derivative with respect to s? Radical t, that's a constant. What's the derivative with respect to t? That means s is constant. Think of that as t to the half. So it would be 1/2 s t to the negative 1/2. 1/2 s t to negative 1/2. So rewriting it, it's radical t s over 2 radical t. Okay, that's the gradient anywhere. Now we want it particularly at the point 2, 4. Obviously, if you have a different point, you have a different gradient. I mean, that's just like in Calc 1. If you have a derivative function, you get a different slope depending on where you're at, right? If x is 2 or 4 or 7 or -80, you get different values. So what's the gradient at 2, 4? I just plug in 2, 4. So put a 4 here, square root of 4 is 2. Put a 2 here and a 4 here. You get 2 over 2 radical 4, that's 1/2. Okay, so the gradient vector at that particular point of 2, 4 is 2, 1/2. All right, so the derivative in the direction of g, sorry, I put del there, that should be d, derivative. Derivative g in the direction of u. Okay, notice how far we've come since Calc 1. Calc 1, all you did was dy dx, rate of change of y with respect to x. Okay, then last section, we did a partial with respect to x, only in the x direction coming right out of you, partial with respect to y going to the right. Now we can go any direction. Okay, so what's the derivative of the function in the direction of u? In the direction of 2 radical 5, negative 1 radical 5. It's very powerful. You want the derivative that way, or 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 whatever. Okay, so it's del f dot u. So the gradient vector dot the unit vector. So 2 1/2, which I just got over here, dot 2 radical 5, negative 1 radical 5. So 2 times 2 radical 5, 2 over radical 5 is 4 over radical 5. And then 1/2 times negative 1 over radical 5 is negative 1 over 2 radical 5. Okay, a little bit of algebra. 7 over 2 radical 5. Okay, I multiply top and bottom here by 2. Usually we don't bother rationalizing the denominator here. Okay, 7 radical 5 over 2 times 5. I don't really see that there's much of an advantage in doing that, so I didn't bother to do it. Okay. All right, and 15 is a 3-dimensional version, right? But it's the same thing. Okay, so 15, find a directional derivative of the function at the given point in the direction of the vector v. So f of x, y, z is x squared y plus y squared z at the point 1, 2, 3, and the vector is 2, negative 1, 2. Okay, that's the direction, but you need to make that into a unit vector. Okay. So the vector direction is 2, negative 1, 2. The unit vector is 2/3, negative 1/3, 2/3. I trust you can figure that out. The magnitude of this vector is 3. Okay, I decided not to do it here. Hopefully you can figure it out. I can talk about it. Let's see, square root of 4 plus 1 plus 4. Is that right? Which is 9. Square root of 9 is 3. So this is a unit vector. 2/3, negative 1/3, 2/3. By the way, double check, what's the magnitude of this vector? You hope it's 1, okay? So what's 2/3 squared? 4/9. Negative 1/3 squared, 1/9. 2/3 squared, again, is 4/9. Add them all up, 4/9 plus 1/9 plus 4/9 is 1. Square root of 1 is 1. So this is the unit vector. Okay, the gradient vector, sometimes written as grad, G-R-A-D, but it's shorter to just write the triangle. So grad f is fx, fy, fz. So derivative with respect to x, 2xy, and this doesn't have any x, so that's 0, so 2xy. And partial with respect to y is x squared plus 2yz. Then the partial with respect to z, that doesn't have a z, so that's nothing. And that's going to be y squared. So that's the gradient anywhere. Now what's the gradient at the given point 1, 2, 3? So I plug in 1, 2, 3. So 2 times 1 times 2 is 4. Let's see, 1 plus 2 times 3. And then y squared is 2 squared. So that comes out to be 4, 13, 4. So the derivative of f in the direction of u, duf, is a dot product of this gradient vector and the directional unit vector. So 4, 13, 4 dot 2/3, negative 1/3, 2/3. Okay, so dot product. That times that, 8/3. 13 times negative 1/3 is negative 13/3. 4 times 2/3 is 8/3. Add them all up, you get 1. Okay. So the rate of change of the function in that one specific direction is 1. Okay. And 19 is worded a little bit funny. I think you can get it. Find the directional derivative of f of xy is square root of xy at 2, 8 in the direction of q, 5, 4. So you're going from 2, 8 to 5, 4. So that gives you a direction. So get the direction vector and change it to a unit vector. Okay. All right, so here's f of x. I'm going to write it as x to the 1/2, y to the 1/2. That's probably easier for taking derivatives. Okay, how far is it, or sorry, what's the direction vector from 2, 8 to 5, 4? So delta x is 3, delta y is -4, right? To go from 2 to 5, you add 3. To go from 8 to 4, you drop 4. And that's our famous 3, 4, 5 triangle, right? Or if you don't know that, just go straight to square root of 3 squared plus -4 squared, which is the same as 4 squared. That's 5. So the unit vector is 3/5, -4/5, right? Okay, grad f, gradient vector, del f, it's fx, fy. So derivative with respect to x, 1/2, x to the -1/2, y to the 1/2. Derivative with respect to y, well, it's similar, 1/2, x to the 1/2, y to the -1/2. Okay, and then write it in radical form. This is the same thing as 1/2 square root of y over x, right? Y to the 1/2 is square root of y, and that means x to the 1/2 square root on the bottom. And here's just reverse. So the y component is 1/2 square root of x over y. Okay, now I plug in 2 and 8. They tell me the point is 2, 8. So 2 for x, 8 for y. 8 over 2 is 4. Square root of 4 is 2, so 1/2 times 2. Flip it, it's 1 square root of, that would be 2 over 8, which is 1/4. Square root of 1/4 is a half. 1/2 times 1/2. So that comes out to be 2 times a half is 1. Half times a half is a quarter. So the gradient vector is 1, 1/4. All right, so the derivative of f in the direction of the unit vector is del f dot u. So 1, 1/4 dot product with 3/5, -4/5. And yeah, I messed up here. What else is new? That's 3/5, and then minus 1/4 times a -4/5 is 1/5. So the answer is 2/5. So the rate of change of the function in that one particular direction is 2/5. Okay, so there we go. Okay. All right, then the next set of problems. Find the maximum rate of change of f at the given point and the direction in which it occurs. Okay. So for those problems, I'm doing this theorem. Which direction is the maximum rate of change? The direction of the gradient. What is the maximum rate of change? The magnitude of the gradient. Okay. So here we go. Okay, 21. F of xy is 4y radical x at 4, 1. Treat this as 4y x to the 1/2. See how powerful this is. Here's a function, z equals f of xy. It gives you a 3-dimensional shape, like you're on a hillside. Okay. And you're at one particular point of that hillside, right? It's curved, whatever. At that one point, which direction would give me the maximum rate of change? Okay. You're walking on a path. Okay. Which way gives the maximum rate of change? So I find the gradient vector. Del f is fx, fy. So derivative with respect to x, treat it as 4y x to the 1/2. So 1/2 comes down, hits the 4y, that's 2y, x to the -1/2. And derivative with respect to y, just drop the y, so 4 radical x. 2y over radical x, 4 radical x. Now I plug in 4, 1. So 4 for x, 1 for y, 4 for x. So that's 2 times 1, which is 2, over square root of 4, which is 2. And then 4 times square root of 4, 4 times 2. So that's 1, 8. Right? So what's the maximum rate of change? The magnitude of this vector. So square root of 1 squared plus 8 squared, radical 65, which is a little bit more than 8. 8 points, 1 maybe. And what's the direction that I head toward? The direction is 1, 8. You don't have to make this into a unit vector, although it's not wrong if you do. It's extra work. Okay. Right. If you have a direction, okay, you could have any scalar multiple of that direction, or a positive scalar multiple of that direction. So if I say the direction is 1080 or 1 million, 8 million, that's basically the same direction, right? Because you could even say 0.001, 0.008. It's a tiny little vector, but it still gives you the direction. It tells you which direction to go, right? Okay. So that's it. And then here's a 3-dimensional one, 25. F of x, y, z is x over y plus z at 8, 1, 3. Okay. And again, it's best to think of it as x, y plus z to the -1. That's y plus z -1. Okay, so I figure out the gradient vector, partial with respect to x, partial with respect to y, partial with respect to z. Now, if I treat it as x times y plus z to the -1, that's a -1 there. Sorry, y plus z -1. Derivative with respect to x, just drop the x. So it's y plus z to the -1, 1 over y plus z. Derivative with respect to y, well, -1 times x is -x. Y plus z to the -2 times the derivative of the inside with respect to y, but that's 1. And then the partial with respect to z is the same thing, right? Again, it's -1 times x, -x, y plus z to the -2 times the derivative of the inside with respect to z, that's also 1. So there we have it. So here's the gradient vector. And now I just plug in 8, 1, 3. So that's 1 plus 3, which is 1/4. 8 goes on top, 8 goes on top. Let's see, 1 plus 3 is 4, 4 squared is 16. Same thing for that. So 1/4, -1/2, -1/2. Right, so what's the maximum rate of change? Square root of this thing squared plus this thing squared plus this thing squared. So 1/16 plus 1/4 plus 1/4, which is 9/16 or 3/4. Okay, so the maximum rate of change is 3/4. What's the direction? The direction I should head is 1/4, -1/2, -1/2. Now, technically that qualifies as an answer, but usually whenever possible, you like to have integers. So I just multiplied all of these by 4. That's why I said or multiply by 4, 1, -2, -2, just to get nicer numbers. Okay. And I guess you could say 1 over 400, -1 over 200, -1 over 200. That would be correct, but no need to be that funny. But it's normally nice to make it into a nice vector, so to speak. Okay. Right, so that's the idea. Okay, let's see, 33. Suppose over a certain region of space, the electrical potential is given by V of xyz is 5x squared minus 3xy plus xyz. Find the rate of change of the potential at P of 3, 4, 5 in the direction of vector V I plus j minus k. In which direction does V change most rapidly, and what is the maximum rate of change? So same idea. This is for electric potential for you physics people, perhaps. Okay, so you have an electric field in space. Okay, you're at one particular point in space, 3, 4, 5. Which direction gives me the maximum rate of change, as it were? Okay. So first they asked for a directional derivative. Okay, they told me I plus j minus k, that's 1, 1, -1. Turn it into a unit vector. So it's 1, 1, -1 over radical 3, right? That's easy. Square root of 1 plus 1 plus 1. So unit vector is 1, 1, -1 over radical 3. And we're at the point 3, 4, 5. So first we need the gradient vector, del v, same as del f, which is v sub x v sub y, v sub z. Okay, partial with respect to x. Let's see, 10x minus 3y plus yz. 10x minus 3y plus yz. Partial with respect to y. 0 minus 3x plus xz. Partial with respect to z. 0, 0, xy. Okay. And now I just plug in 3, 4, 5. The given point was 3, 4, 5. So x is 3, y is 4, and z is 5. So 10 times 3 minus 3 times 4 plus 4 times 5, comma, negative 3 times 3 plus 3 times 5, comma, 3 times 4. So 10 times 3 is 30, minus 3 times 4 is 12, plus 4 times 5 is 20, negative 9 plus 15, and 12. 38, 6, 12. So what's the maximum rate of change? The magnitude of 38, 6, 12. So it's the square root of 38 squared plus 6 squared plus 12 squared. Comes out to be square root of 1624, or 2 radical 406. What's the direction that you should head for? 38, 6, 12, the gradient vector. Okay, I actually didn't do part A yet. I wanted to focus on this more, but part A, find the directional derivative of the vector in the specific direction of 1, 1, negative 1. So I take the dot product of my gradient vector, 38, 6, 12, with 1, 1, negative 1 over radical 3. That's all. So it's 38 plus 6 minus 12 over radical 3, 32 over radical 3. Okay, so if I go specifically in that direction, that's the rate of change. But what's the maximum rate of change? This thing. And which direction do I go for that maximum? In the direction of 38, 6, 12. Okay. All right, so that's that. And I just have 41 and 45 left. And I'm actually done with the section. I can get started with the next section. Tangent planes to level surfaces. It's not too bad. So I use that thing. 41. Find the equations of the tangent plane and a normal line to the given surface at the specified point. Okay, so 41, 2x minus 2 squared plus y minus 1 squared plus z minus 3 squared equals 10 at the point 3, 3, 5. Okay. Side note, this is an ellipsoid. If this did not have a 2 there, all the coefficients are 1, you would actually have a sphere centered at 2, 1, 3 radius of radical 10. This 2 fouls it up, so to speak. You have an ellipsoid. It still has a center of 2, 1, and 3, but it's going to be bulging in one side. But anyway, we don't really need to know that. All right, so I find the gradient vector del f. Okay, you could subtract the 10. It's supposed to be technically equal to 0, but equal to 10, it doesn't matter because the derivative of 10 is 0 anyway. Okay, so partial with respect to x, 4 times x minus 2. Partial with respect to y, 2 times y minus 1. Partial with respect to z, 2 times z minus 3. And the given point was 3, 3, 5. Put a 3 there, 4 times 1 is 4. Put a 3 there, 2 times 2 is 4. Put a 5 here, 2 times 2 is 4. The gradient vector is 4, 4, 4. So what's the equation of the tangent plane? Fx, x minus x0, plus fy, y minus y0, plus fz, z minus z0, equals 0. So 4 times x minus 3 plus 4 times y minus 3 plus 4 times z minus 5 equals 0. Okay, technically that's correct. You can make it nicer. You can divide both sides by 4 or factor out the 4. So you have x minus 3 plus y minus 3 plus z minus 5 equals 0. And if you clean that up, that's x plus y plus z equals 11. Okay. For the normal line, you just go x minus 3 divided by fx, 4, equals y minus 3 over fy, 4, equals z minus 5 over fz, 4. Okay. This is acceptable, but this is nicer. Multiply them all by 4, right? So you basically have x minus 3 equals y minus 3 equals z minus 5. And then if you add 3 to all of them, this is the nicest way to write it. X equals y equals z minus 2. So there you go. Okay. All right, 45, and then I'm done. Then I'll get started with the next section, which is pretty heavy duty. It's on maximum and minimum values. But yeah, let me knock out 45 and then we're done with that. Okay, x plus y plus z equals e to the xyz at 0, 0, 1. Okay, this one you definitely have to get all on one side. So you kind of have to decide which one do you want positive and which one do you want negative. I'd rather have the exponential as positive. So I move all of these over and made all these negative. Okay. Now you say, could I move this over? Yeah, you could. You would have fewer negative signs. Still, I think most of us are less comfortable with e to the x, y, z compared to, negative x, negative y, negative z. Those are so easy, they don't bother me. So I'd rather go with f of x, y, z as e to the x, y, z minus x minus y minus z, like that. Okay. All right, so del f gradient vector is fx, fy, fz. So derivative with respect to x. Well, these are easy. That's going to be minus 1, minus 1, minus 1, right? So you okay, the minus 1, right? Differentiate with respect to x. For these three, it'll be a minus 1. For these three with respect to y, it'll be minus 1. And for these three with respect to z, it will also be minus 1. Okay, so the only thing I have to worry about is this. And you can see that's why I want it to be positive. So differentiate with respect to x, it'll be e to the xyz times the derivative of this with respect to x, that would be yz. Similarly, if I differentiate with respect to y, let's see. Yeah, I would have xz e to the xyz. And differentiate with respect to z, I would have xy e to the xyz minus 1. Okay. So that's what I have over there. All right, now I want the gradient at 0, 0, 1. Plug in 0 for x, 0 for y, 1 for z. Let's see, if y is 0, that's gone. X is 0, that's gone. X is 0, that's gone. So it's negative 1, negative 1, negative 1. All right, so fx, x minus x0, plus fy, y minus y0, plus fz, z minus z0. Okay. And if I multiply both sides by negative 1, the coefficients are 1. So it's x plus y plus z minus 1 equals 0, or x plus y plus z equals 1. Very nice. And then symmetric equations for the normal line. Just go x minus 0 divided by that, negative 1, equals y minus 0 divided by that, negative 1, equals z minus 1 divided by negative 1. And you can just multiply all of them by negative 1. So you have x equals y equals z minus 1. And that is that. Okay. All right, and I'm now officially done with 14.6, folks. So I'm going to start 14.7. Okay. So 14.7. So this schedule is all fouled up now. Okay, so I'll start some of 14.7. And let's see what it's all about. maximum and minimum values. Remember doing max and min in Calc 1, right? Okay, maximum, minimum, derivative is equal to 0 at a maximum or a minimum, right? Okay, so we have similar concepts, but much more difficult. Okay, and here's something that's computer generated. Obviously, I can't draw that. But that looks like an absolute max, local max, absolute min, local min, and so forth, right? In a three-dimensional system. So what can I say about max and min? Okay, let's look at this top point. What will be the rate of change in the x direction? Should be 0. How about the rate of change in the y direction? Also 0. How about a minimum point right here? What's the rate of change in the x direction coming out this way? It should be 0. Likewise, what's the rate of change in the y direction? It should also be 0. So for max and min, page 960, Theorem 2. If f has a local max or min at a point A, B, and the first order partial derivatives of f exist there, they always will for us, then fx at AB is 0, and fy at AB is also 0. The rate of change in the x direction and the y direction are 0. Okay. Here's a very formal definition of a maximum or minimum. You can read it or not. I'm just going to go by your intuition. It's a high point, it's a low point. Okay. So if you stumble over all of this, it's correct. There's nothing wrong with it, but I don't think it really helps to talk about it, frankly. Okay. If you're at a high point, then the only other place you can go is down. And if you're at a bottom point, then the only place you can go is up. All right, so we'll have this. Fx is 0, Fy is 0. You can put this on your cheat sheet, but frankly, I don't think you need to. I mean, those are the same rules that you had in Calc 1, right? Okay, what is much harder, and again, we'll state it without proof, the book goes over an outline of a proof, is the second derivatives test. Notice we said second derivatives, not second derivative, because we know there's more than one second derivative, right? Now, if you have a function x and y, you're going to have fxx, fyy, fxy, and fyx, although we now know that fxy and fyx are the same. Okay, so page 961, you definitely may want to put this on your next cheat sheet. Okay, second derivatives test. So here's the way this works. This is much more complicated than in Calc 1. See, what happened in Calc 1? You did concavity, right? Remember concavity, concave up, concave down. And that told you maximum or minimum, right? It's much more complicated in this case. Okay, first you have to evaluate something called the D. Okay, and it doesn't really stand for anything. It doesn't stand for derivative. Okay, it's just some quantity. It's defined as this: fxx, fyy minus fxy squared. Okay, you can have the a, b there, but it just tells you to plug in. In fact, I'm going to write in my book, if you don't mind. So I'm going to write it like this: fxx, fyy minus fxy quantity squared. Okay, so this is the D. It's the same as this. It's a little bit faster to write. You basically put down all the partials, right? It's fxx, fyy minus fxy, fyx, but fxy and fyx are the same. And here are the rules. If D is positive and fxx is positive, then you have a minimum. B, D is positive, fxx is less than 0. You have a maximum. If D is less than 0, you have neither a maximum nor a minimum. Okay. Case C, you have something called a saddle point. Okay. A saddle point, you're at a maximum in one direction and a minimum in the other. I think I mentioned that before. You take a look at figure 3. Okay. At the origin, this is a saddle point. Okay, because if you look in this direction, right, it's a minimum. But if you look this way, it's a maximum. And let's see, how can I prove it? Yeah, if you remember when we were doing traces, right? We did traces. If it is the trace in the x equals 0 or yz plane, z equals y squared is a parabola opening up. But if you trace in the y equals 0 or the xz plane, z equals negative x squared, that's a parabola opening down. So you can see right here that it's a maximum. So it's a maximum facing one way, right? But it's a minimum if you face another way. And we never saw that in Calc 1, right? Calc 1, that was never an issue. Okay, and just for fun, they're showing a weird picture here of someone hiking. And I guess they're trying to illustrate, it's kind of scary if you ask me. Okay, but that point here looks like a saddle point. Okay, so where this guy's hiking, if you go this way, that's a minimum. But if you go the other way, it's a maximum. Right? So that point would be a saddle point. Right? Because if you look in this direction, in the x direction, that's a minimum. But if you look in the y direction, that's a maximum. Okay. So that's called a saddle point. All right, definitely put this on your cheat sheet. Okay. What happens if d equals 0? The test fails. We've seen cases where the test fails before, right? Remember when you're doing all of your, in Calc 2, your sequences and series, sometimes a test failed, right? You were doing stuff like ratio tests, root tests, remember all that stuff? Okay, and sometimes a test failed. So if d equals 0, the test fails. You could still have a max, you could still have a min, you could have a saddle point, you could have none of them. So if d equals 0, you don't know, you just have to try something else, is I guess the best way to say that. Okay. So we're doing some problems with that. Okay. Now, those are only the easy problems. Okay. Harder problems, absolute max and min on a closed set. Okay. What's a closed set? Something like this. These are not closed. Okay. There's a boundary and you're counting the boundary. I guess theoretically, you know, if this is your home, it's all enclosed, right? You can't get in. Hopefully nobody is a burglar or whatever, right? These sets are not closed. There's a place that you can get in, right? There's a tiny little hole at the top of that circle, which means it's not closed. You can sneak in that way, right? Or there's no way to get in. There's a way to get in here and here and here, okay? So much harder is absolute max and min on a closed set. Now, by analogy, way back in Calc 1, remember you did stuff like absolute max and min on a closed interval? If you have a closed interval from A to B and f is continuous, then f must attain a maximum or minimum value on a closed interval, right? So it was not necessarily true if you had A, B like that, or A, B like that, or A, B like that. Those are not closed intervals, right? It had to be a closed set, right? So remember doing stuff like that? So what you would do is find critical points, right? So wherever the derivative is 0, and then you'd also have to check the boundary. Remember doing stuff like that? Okay. The boundary might have the maximum or minimum just because it was the boundary, not because the derivative was 0, but just because it's a boundary, it might be the highest or the lowest point. Something similar happens here, only you may have a much more complicated boundary, right? You might have to consider an entire circle or square or whatever. Okay. That was part of something called the extreme value theorem, page 965. Extreme value theorem. Okay. If f is continuous on a closed bounded set in R2, then f attains an absolute max and absolute minimum at some point within that region. Okay, you don't really have to write that. What you do want to write down is this, page 966. To find the absolute maximum and minimum values of a continuous function f on a closed bounded set D. Okay. Find the values of f at the critical points, and then find the extreme values on the boundary. The boundary is like the two endpoints in Calc 1. The largest of these is the absolute max. The smaller of these is the absolute minimum. This is the higher dimension of the closed interval problems that you had. I believe is in chapter 4. Okay, I think I got time. Let me show that to you quick and then we'll break. This is analogous to, hope you guys remember this. Yeah, remember doing stuff like this a long time ago? Chapter 4. Find the absolute max and min on the closed interval. Notice there's a closed interval, right? And they give you the closed interval method. Yeah. Page 281. Find the values of f of the critical numbers. Find the values at the endpoints. Okay, the largest, steps 1 and 2 is the absolute max. The smallest is absolute min. Okay, we're in a higher dimension now. It's not just 2 points. It's an entire boundary. So that's the analogy. Find the values of at the critical points and the values at the boundary. Okay, this could get really long. I mean, really long. Okay, so I did not give you that many problems involving that. Okay, so we'll look at this after the break. We'll get started with some problems here after the break. Okay, so let's stop 6:58. How about 7:10? Okay, we'll break until 7:10. I'll put that in the chat also. Okay. All right, folks, let's pick up. We were. Okay, I will do some of the quote unquote easier problems. Some problems from the 5 to 17 set. Okay, I think I'll hold off on 31 to 37, 41 to 45 until next time. So I'll do some of these and then I'll stop and then I'll give you a quiz and we're done. Okay. And it looks like it's not that long of an assignment, but it is. Believe me, some of those problems are quite long. Now think back when you were in Calc 1 and you said, oh yeah, I know how to find maximum and minimum, set the derivative equal to 0 and so on, right? It's not that easy when you're trying to set fx and fy both equal to 0 at the same time. It depends on what the function is. Okay, so I'll show you, give you a taste of what that's like. Okay, so I'll just do some of the problems here and these get harder. Okay, all right. Okay, so let's take a look. Now let's see, show you what we got. 5 to 17 odd. Okay, so here they are. Find local max and min and saddle points of the function. If you have three-dimensional graphing software, blah, okay, we skipped that. So these are all function of x and y. So they have some shape. Okay, they're functions. So you pick any point in the floor, you go up and down, it's only going to touch one point. Okay, so where's the max and min? Okay, completely analogous to what you did in Calc 1. Calc 1, find max and min. Now you're in 3D. I don't know if I can just take this and curve it to some three-dimensional object, right? Find maxima and minima on something like that, or that hillside thing that we had. Okay, so we are doing this. Set fx and fy equal to 0. And then the second derivatives test, you find the d and then go by the chart there. All right, so here we go. Oh yeah, so again, show you the problems. It was 5 to 17, I think it was. Oh, there. Okay, and then what else did we have? 31 to 37, which is quote unquote only 4 problems, but these could get really long. Find the absolute max and min of the function in the set D. And then what, 41 to 45 are some word problems. Applied max and 41, 43, 45. Yeah, there we go here. Okay. So here we go. You're given some function. Don't worry about graphing it, but it has a graph in 3D. You can get a 3D grapher for that. Where's maximum, where's minimum, saddle points, and so forth. Okay. Here we go. Number 5. F of xy is x squared plus xy plus y squared plus y. So find fx and fy, partial with respect to x, 2x plus y. Partial with respect to y, nothing, x plus 2y plus 1. I need the second derivatives to do the second derivatives test. All of them. You need fxx, fyy, fxy, and fyx, but fxy and fyx are the same. So fxx, take the partial with respect to x, and I differentiate with respect to x, 2. Fyy, take the partial with respect to y, here it is, and differentiate with respect to y, 2. Then the mixed partials, fxy, take the derivative with respect to x and now differentiate with respect to y, 1. And a double check, if I take fyx, take the derivative with respect to y and now differentiate with respect to x, it's also 1. So there we go. Okay, I set this equal to 0. I set this equal to 0. They both have to be true. Okay, so in other words, 2x plus y equals 0. And this has to be 0 also at the same time. Okay, so 2x plus y equals 0 means y equals negative 2x. Plug that in to here. So x plus 2y, it's basically a system of 2 equations and 2 unknowns. Okay, x plus 2y, but y I now know has to be negative 2x plus 1 equals 0. Okay, a little bit of algebra. X minus 4x is negative 3x plus 1 equals 0. That means x is 1/3. Plug in 1, y is negative 2/3. Okay, so the only critical number that I have is 1/3, negative 2/3. Okay, do I have a maximum or minimum or neither? That's where I do the D stuff. Okay, so I'm following this algorithm. Okay, it's a lot harder to memorize. So, this is pretty easy, even to memorize, right? Set fx and fy equal to 0. That was just like Calc 1, right? Set the derivative equal to 0. So here you set the first derivatives, fx and fy, both equal to 0. Okay, after all, if you're at either a maximum or minimum, if you take the derivative this way, it should be 0. And you take the derivative this way, it should also be 0. Okay, harder is the second derivatives test. So first you figure out the D and check if you have case A, B, or C. Okay, so D by definition is fxx fyy minus fxy squared. Okay, so fxx came out to be 2. Fyy also was 2. Minus f of xy squared, that's 1 squared. So it's 2 times 2 minus 1 squared, which is 3. That's greater than 0. All right, the D is greater than 0. That means I'm either at case A or B. It's not C, right? And then it says, get the sign of fxx. So fxx, what was fxx? Where'd it go? It's 2. That's greater than 0. Therefore, I have a minimum. Okay, so I have a minimum at f of 1/3, negative 2/3. And then, yeah, give the minimum value, just plug in. So plug in 1/3 and negative 2/3. I'll spare the agony. You can work it out. It's negative 1/3. That's just like in Calc 1, right? You found the maximum minimum was at x equals 7, but what's the y coordinate? Then you just plug in. Same thing here. Plug in 1/3 and negative 2/3. 1/3, 1/3, negative 2/3, negative 2/3, negative 2/3. You can do it as well as I can or better. Comes out to be negative 1/3, hopefully, unless I messed up. Right, so the critical point is at 1/3, negative 2/3, and the z coordinate is negative 1/3, and that's going to be a minimum. So it looks like there's no maximum. Okay, so that's the first attempt at doing this kind of problem. Okay, think back to in Calc 1, same thing, right? Find maximum and minimum values of a function, right? What's the high point, what's the low point, and so on. Okay, obviously, a lot more involved once you get to multivariable, but same concept. Okay. All right, so I'll just do a few more of these. Okay, problem number 11. There's a lot more variety as to type of problems. See, when you're back in Calc 1, right, after a while you say, oh yeah, I know what to do. It's all pretty much the same, but they're not necessarily all the same in multivariable. Okay, I'll try 11. F of xy is x cubed minus 3x plus 3xy squared. Okay, so what do I do there? Okay, find fx, partial with respect to x. 3x squared minus 3 plus 3y squared. Partial with respect to y, nothing, nothing, 6xy. Then the second derivatives, fxx, differentiate this with respect to x, 6x. Fyy, differentiate this with respect to y, 6x. Fxy or fyx, might be easier to look at this one, differentiate with respect to x, 6y. But double check, what's the derivative of this with respect to y? Nothing, nothing, 6y, it matches. Okay, now this has to equal 0, and this also has to equal 0. In other words, you're solving 3x squared minus 3 plus 3y squared equals 0, and 6xy equals 0. So there's a much wider variety of things that can happen. Okay, I think it's easier to look at Fy. If 6xy equals 0, that means either x is 0 or y is 0, correct? 6xy equals 0, x is 0 or y is 0. So treat them separately. Okay, x equals 0, put a 0 right there. Then I have negative 3 plus 3y squared equals 0. Little bit of algebra, y squared equals 1, y is plus or minus 1. So I have 0, comma, plus or minus 1. Now try y equals 0. Put a 0 right there. I have 3x squared minus 3 is 0. Little bit of algebra, x is plus or minus 1. So I have 4 critical points. 0, 1, 0, negative 1, negative 1, 0, and 1, 0. Okay? Or think of your 4 basic points on the unit circle, except you're not considering the entire unit circle. Okay, so which one of these are maximum, minimum, or neither? Okay, so I have to figure out the D. D is fxx, fyy minus fxy squared. Okay, so what was fxx? 6x. Fyy was also 6x. Minus fxy squared, 6y quantity squared. So I get 36x squared minus 36y squared. Okay, the D at 0, comma, plus or minus 1. Put a 0 there. Either a plus or minus 1 there is going to be negative 36. That means I have a saddle point. That's case 3. Or C. If D is less than 0, we have neither a local maximum or min, but we have a saddle point. Like that picture there, figure 3. Origin right there. It's a saddle point. D of plus or minus 1, 0. Put either a plus or minus 1 there and a 0 there. You get 36. So that's going to be either case 1 or 2. Then I look at fxx by rule. Okay. So if the D is positive on case either A or B, okay, then case A, fxx is greater than 0, minimum. Fxx less than 0 is a maximum. And by the way, that sounded like Calc 1, right? In Calc 1, second derivative positive meant the minimum. Second derivative negative meant the maximum. So that part is somewhat consistent. Okay, so at 1, 0. So what's fxx at 1, 0? I plug in 1, and there's no 0 to plug in, so I get 6. That means that's a minimum. Fxx at negative 1, 0. So plug in negative 1, 0 to fxx. I get negative 6. That's a maximum. Okay, so I have this thing completely analyzed. It looks like out of those 4 critical points, I have 1 maximum, 1 minimum, and 2 saddle points. So very rich variety. You never had such a thing as a saddle point in Calc 1, but now you can have a saddle point. Once you get to 3 dimensions, you could look this way, it's a maximum, but you could look this way, it's a minimum, right? Like a saddle, like the saddle of a horse. Okay, then I plug in f of 1, 0 back at the beginning, 1 and 0 wipes that out, so that gives me -2. And -1, 0, let's see, -1, 0. Put -1 there, -1 there, that's -1 plus 3, which is 2, and that's 0. That's a max. That's interesting. So 1, 0 is a minimum, -1, 0, 2 is a maximum. Okay. I guess it's not so interesting after all. I thought they were the same thing, but never mind. Okay, f of 0 plus or minus 1. Okay, all of these have an x. So I plug in 0, you have a 0. Okay, so we have it all. So as a ordered triple, as x, y, z, 1, 0, -2 is a minimum. 1 out, nowhere y, and then 2 down. That's going to be a minimum. 1 into the board or into the plane, 0, and then 2 up. That's a maximum. And then 0, -1, 0. That will be 1 unit to the left. And 0, 1, 0, 1 unit to the right from the origin. Those are both saddle points. Okay. So quite interesting what's going on here. All right. 15. Somewhat interesting. Actually comes out fairly easy. 15. F of xy is e to the x cosine y. E to the x cosine y. This one's very fast, actually. Okay, derivative with respect to x. E to the x cosine y. Same thing. Derivative with respect to y. That means e to the x is constant, so it's e to the x times negative sine y. Okay. I didn't bother doing the second derivatives for a reason. I know this has to be 0 and this has to be 0, right? Okay, so e to the x cosine y and negative e to the x sine y have to be 0. Now, what do we know about e to the x? It's always what sign? S-I-G-N. Positive. So the only way this can be 0 is if cosine y is 0 and sine of y is also 0. Do we know any angle where the cosine is 0 and the sine of y is also 0? No such thing. So it can't. We're done. There's no critical points. No maximum, no minimum, no saddle points. I didn't bother doing the second derivative because we don't have to. There's no critical points. Okay, remember, both of these have to be true. In order for both to be true, e to the x cannot be 0. That means cosine y and sine of y both have to be 0, but there's no such angle like that, right? I mean, sine of what angle is 0? Well, like 0, pi, 2 pi, but the cosine of those angles isn't going to be 0. So we're done. That was pretty fast. Okay. And then what do we have? 17. And I think that's the last one of this type that I'll show you. I'll give you a little bit of a taste of the harder problems, and then I'll stop, and then we'll take our quiz, and we're done. Okay, so 17, please. F of xy is xy plus e to the negative xy. Okay, fx, y plus e to the negative xy times the derivative of the exponent with respect to x, that would be a negative y. So it's y minus y e to the negative xy. Factor out the y, and I have 1 minus e to the xy. Okay, fy, differential with respect to y, x plus e to the negative xy times the derivative of the exponent with respect to y, negative x. Now factor out the x, 1 minus e to the negative xy. Okay. Incidentally, both of these have to be true. That means y equals 0 or x equals 0. And by the way, if you look at this second expression, 1 minus e to the negative xy, maybe the best way to think of it is I have to set this thing equal to 0, right? Let me cover this up. E to what exponent gives me 1? 0. That means negative xy is 0, or that means x is 0 or y is 0. So we get the same thing, basically. So either x is 0 or y is 0. All right, then I do fxx. So fxx. Okay, so let's see, where are we? Derivative with respect to x. So leave the y alone. Derivative of 1 is 0. Derivative of negative e to the negative xy is itself times the derivative of the exponent with respect to x, which is negative y. Okay, I get a double negative. So I have y times y, or y squared e to the negative xy. Similarly, fyy, differentiate with respect to y, leave the x alone. Derivative of 1 is 0. Derivative of negative e to the negative xy is itself times a negative x. I would have a double negative again. So it's x squared e to negative xy. Okay, and then fxy. Okay, so differentiate with respect to y. That's a little harder. So product rule. First times derivative of the second. So I did y times derivative of the second. Derivative of the second is negative e to the negative xy times a negative x. Plus the second, 1 minus e to the negative xy times the derivative of the first with respect to y, but that's just 1. Okay. So I get this mess here. Okay, D should have squared here. Okay, fxx fyy minus f of xy squared. Okay. Now, if you work all this out, I think you ended up with 0. Let's see. Can't convince myself of that right now. Let's see, x squared, y squared, e to negative 2xy. Okay, I came up with this, although I left out some steps here. I'm not sure how I came to that conclusion that quickly, that it came out to be 0. Anyway, fxx fyy, x squared, y squared, e to negative 2xy. And I seem to be missing some steps here, but if I square this, I think I ended up with 0. Okay, which basically means inconclusive. Okay, that would have been the situation where it's inconclusive. Sorry, I seem to have missed some steps there. But that seemed to be the case where note 2. Let's see where to go. Yeah, note 2, D is equal to 0. The test gives no information. Okay, well, let's assume I got it correct, which, as you probably know by now, is not a safe assumption. But I'm not sure how I got that or I left off some steps. But theoretically, if I'm correct, if fxx, fyy minus this thing squared is indeed 0, okay, then this is what I did. Okay, if either x is 0 or y is 0, okay, either x is 0 or y is 0, that's 0, that's 0, I would have 1. Okay, if either x is 0 or y is 0. Then I moved off, quote unquote, a little bit, like 0.1, 0.1. Okay. 0.1, 0.1, or 0.1, 0.1. Okay, if I plugged in, you end up with something that's bigger than 1. Okay. What that means is that f of xy equals 1 is a minimum at all the points where either x is 0 or y is 0. So that's basically on the x and y axes. Anywhere on the x and y axis, you have a minimum. If I go off a little bit here or here or here or here or here, you'll get numbers that are bigger than 1. Okay, so all of these points would end up being minimum points in this particular case. Okay, assuming I did this correctly. Okay, so the way I did that was just, I literally moved off a little bit. Okay, so I moved off a little bit, it got higher, so that told me that I have minimum. Okay. All right, I'm done, except I'm gonna introduce you, it just saved me time next Tuesday, and then I'll stop and give you the quiz. For 31 to 37, to show you what's happening. Find the absolute max and min of the function on the set D. So I'll show you the setup for 31. f of xy is x squared plus y squared minus 2x. D is a closed triangular region with vertices 2, 0, 0, 2, and 0, negative 2. Okay, I won't do it, but I'll actually show you what's happening. I'll save it for next time. But you are going to follow this, page 966. Find the critical points. Find the extreme values on the boundary. So we have to maximize and minimize on the boundary. And then the largest of all those would be the absolute max. The smallest of all of those would be the absolute min. So let me show you the picture and then I'll stop. Here's the function. Then it said the closed triangular region, including 0, 2, 2, 0, and 0, negative 2. So the boundary is this triangle that I have to check. So I'll find the critical points. That's easy. Set fx equal to 0, fy equal to 0. But then I have to check the entire boundary. Remember in Calc 1, you just check 2 endpoints. You're going from A to B. Here, you need to check this entire boundary. Okay, now what is this boundary? This is x equals 0 as y goes from negative 2 to 2. Little bit of algebra. This has a slope of negative 1, y-intercept of 2, y equals negative x plus 2 as x goes from 0 to 2. Double check. What do you get when you plug in 0? 2. What do you get when you plug in 2? 0. And then what is this part? Slope is 1, y-intercept is negative 2. Y equals x minus 2 as x goes from 0 to 2. What do you get when you plug in 0? Negative 2. What do you get when you plug in 2? 0. Okay. So as soon as I find the critical points, that's easy, the function values. Then I have to check what happens when x is 0, what happens when y is negative x plus 2, what happens when y equals x minus 2. It can get really long, as you can imagine. Okay, so we're going to set fx and fy equal to 0. That's the easy part. The harder part is to analyze x equals 0, and then analyze y equals 2 minus x, and then analyze x minus 2 also. All right, got it here, y equals x minus 2. Okay, and we'll do that next time. Okay, but as far as coverage is concerned, we're doing pretty good. So 14.7, I'm done with the first part, the 5 to 17. So I have 31 to 37 and 41 to 45. And then I can probably do some of 14.8 also. So it looks like I'll be finished in plenty of time. Okay, so again, a reminder, we're aiming for the next test to be Thursday, the 18th. I might even finish everything by Tuesday, but if not, I still have Thursday. Okay, so we'll save questions and answers for Tuesday, 3/16. I'll give you some question and answer time for that. And then for the actual test, I'll give you the entire class period again. So no questions and answers on the 18th. Anything has to be on the 16th for that. Okay. All right, any questions? Otherwise, we're done. I'll give you a quiz and then we'll call it a day. Okay. So any questions, please? Either put it in the chat or unmute yourself. Although if you unmute yourself, I'm not sure I can hear you. Okay, I don't see anything and I don't hear anything. All right, so quiz time, get your cell phones out or be ready to do a screenshot. Here we go. Okay, given the function f of x, y, z is 3x squared y cubed z to the fourth, find a directional derivative at the point -2, 1, -1 in the direction of 6, -2, 3. Note that the direction given is not a unit vector. You have to make it a unit vector. Number 2, for the same function and the same point, find the maximum rate of change and the direction which gives the maximum rate of change. That direction does not have to be a unit vector. So once you get the direction, you can stop after that. Okay, I'll give you another 15 seconds or so to get this down. Go ahead and get started. And then I'll set your breakout rooms when you're done. Work it all out. Put first and last name of everybody in your group. And that'll do it. Okay, I'll read it again just in case you don't have it. F of x, y, z is 3x squared y cubed z to the fourth. Find a directional derivative at -2, 1, -1 in the direction of 6, -2, 3. Notice the direction is not a unit vector. You know what that means. Then 2, same function, same point. Which direction gives the maximum rate of change and what is that maximum rate of change? Just like we did the first half today. Okay, I will assume everybody has it now. So I will stop the share. I will stop the recording, no longer recording.